Hello, good day, ma'am. I have a question regarding the homework.
Good morning. What kind of question do you have?
So I want to know, like, so the variation, right? You have 1 to 10. So my last two digits is 11. So what should I do?
What is your student ID number, last digit? The
11.
instructions was there. So
My
if your student ID ends with a 3, then you take version 3.
okay. So
If
no.
your student ID number ends with a 0, like 10 or 20, you take number 10. It's all according to the last digit of your student ID.
Okay. So it's
Okay, only
minus
10
11.
versions this time.
Okay. So minus 11. It will be 1, right?
Yes, exactly.
Okay. Thank you, ma'am.
All right, so it's time for us to begin. While we settle this problem, it's time for us to begin. Don't forget to sign. Don't disappear, because at some moment I'll probably ask you to sign again. Before we start, let me check. 14 of you, not everybody will hear that, but I did put the notice in Ortus. That is, because on Friday we have the second midterm examination. Well, formally it's the second half term or the end of semester, not whole semester. Anyway, I call it midterm too because that's easier and simpler. Because last Friday, when we had this 6th unit test, there were people who forgot to notify me that they couldn't because they had another test or another consultation or something. And then there were people who notified me late, and then there were people who didn't notify me at all, and so on and so on. Please let me know if there is a time when you cannot write the midterm second examination. The groups and times will be set accordingly. As I already wrote, the first group might be as early as 10. I am not exactly sure. I don't want to make more than 2 groups, but it will depend on the information you send me. So please, today, tomorrow, or on Wednesday, 3 days for you to let me know if you have another examination, something important on Friday, and therefore you cannot do it at a certain time. Do not tell me when you can. Tell me when you cannot. I will set the times accordingly then. I will try to remember to remind everybody in the end of the lecture. Those who are late and didn't hear what I was saying, don't forget to read the notice in Ortus about notifying me about Friday, because your timing, your group will depend on that. All right, now it's time to deal with functions of several variables. We have a lot of work in 2 lectures. Well, generally, it's 2 or 3. I think we will do quite well with two lectures. So what is a function of 2 variables? What are the derivatives? How do we go about differentiation of functions of 2 variables, and so on, and higher order partial derivatives. So today, basically, how to differentiate a function that depends on more than one variable. So we will start with the general idea of what is a function of 2 or more variables. We know that normally up to this moment, you are used to have the regular old function like y is a function of x. And everybody's happy with that. We have been spending many weeks on these functions. Now, of 2 variables, we might have, for example, the variable z is equal to, it's some function depending on 2 independent variables, x and y, for instance. We might have a function, for instance, I don't know, function w that depends on x1, x2, x3, x4. So for instance, we could have a function z equals x squared plus y squared, for example. this would actually be a paraboloid. We could have a function that is, for instance, 4x1 minus x2 plus 3x3 plus x to the x4, for instance, something like that. These functions, for instance, if the function of one variable reflects maybe a process that depends on only time or only something else, not necessarily a process, so one quantity depending on another, why do we need several variables? For example, we might want to see what a graph of such a function looks like. We can only investigate graphs of functions of two variables, because if we have more than two variables, we cannot even imagine them. So now if you look at this z, okay, I will change the color. Let me see. All right. The Z variable depends on X and on Y. So we can imagine that we have the domain, a part of the XZ plane, some kind of domain, some region. And above this domain, the Z value of each point of the graph is found according to this function of two variables. Basically, a graph of a function of two variables is a surface. For each point x, y, x and y are independent variables, x, y. For each point, we have a z value. So basically, every point on the graph has three coordinates, x, y, z, where z depends on where we are looking. You can imagine this like as a tent or a pavilion, and the height of the ceiling depends on where you are standing when looking upwards. So that explains perhaps the idea of the domain, which is a region of xy plane of a two-variable function. So that might be the most obvious, the physical, the geometrical interpretation of a function of two variables. However, it might be something else. It might be any other things that might depend on two variables. In engineering, it doesn't have to be a location. It could be some certain quantities which define actually the third quantity, not necessarily a geometrical interpretation. If we have a function, for instance, of three variables, that might be applicable to different things in space. For example, three independent variables, x, y, z, might define the location of a point in 3 dimensions, but the function at this point might express, for example, the temperature at that point of the I don't know, whatever space. It could be, for instance, the intensity of the electromagnetic field. It might be many different things. It might be, for example, if you have an object of non-homogeneous density, then it might be the density at that point. So all kinds of things could be defined at different points of space that could change. And then when we talk about functions of more than three variables, they are basically abstract things. They are functions, they are quantities that depend on many other quantities. A lot of this kind of function, for example, like my W function, are used in, for example, economics. In economics, for example, some kind of projected income or some kind of projected revenue or anything else might depend on many things. For example, how much is obtained, how much is spent, and so on and so on. So we have a function where one variable depends on two or more other independent variables. The most common thing that we discuss is, of course, a function of two variables. So now, if we compare the graph of a function of two variables to the graph of a function of a one variable, of just one variable, now you see the graph of a single variable function is some kind of curve. It's two-dimensional, and that's it. Here, the surface, it's in 3 dimensions. We have 3 variables. One is dependent on the others. So when we want to differentiate, if the derivative of the function, as we understand it, simply tells us about the slope, describes the slope of the graph. So what kind of slope is described by any, could be described by any derivatives of a function of two variables? You at any single point, basically, if you want to draw a tangent line, it could go in many directions. It could go in this direction, this direction, this direction. And basically, what's a slope? Slope only works in 2 dimensions. In this situation, we see, yes, the slope is, we know, it's the tangent of this angle. So what about the functions of more than one variable, specifically of 2 variables? We will discuss that today, more or less, and most of all next time. And so if we look at the domain of a function of 2 variables, as we already saw, is a region of the xy plane. So basically, we can consider the xy plane. The xy plane could be considered, let's say, the floor, and the domain would be the region on which we are allowed to stand and look upwards vertically, perpendicular to the floor, for instance. So generally, the domain could be restricted artificially. You will see examples of that next semester when you integrate. There will be double integrals, integration of, of functions of 2 variables as well, just like we differentiate today. You will integrate them in next semester as well. So the domain generally can be considered the set of all those points in the plane of 2 variables. So basically, we denote this plane as R squared. R squared consists of all pairs of points where, of course, x and y are real numbers. So 2-dimensional real number set. Well, 2-dimensional means we have 2 real numbers defining coordinates. So generally, the point in the set R squared, it's the 2-dimensional point in the 2-dimensional plane. However, as I said, the domain is usually some subset, not the whole plane, but a subset. In this case, we say, all right, we cannot find the value of this function if x is 0 or if y is 0. So x cannot be 0 and y cannot be 0, which means we can take the whole plane except the axis. So we see that these axes of coordinates are excluded. You cannot evaluate the function on the axis. However, all the other points of the xy plane belong to the domain. So basically, the domain consists of the 4 separate quadrants of the xy plane, but not the axis. We can understand that when we approach one of the axes, yes, we talk about limits as well, although we will not discuss them in detail today. We can talk about limits in 2 dimensions for 2 variable functions. But imagine that if we approach a point on the y-axis, basically we see that the function value will go off to infinity. It would be an interesting graph. This function would have an interesting graph where the graph, this surface, shoots off to infinity on the axis. And the second function, just 2 examples for the domain, because we have to understand that the 2 variable functions quite often have limited domain, bounded domain. In this case, we see that the radicand, the expression below the square root, has to be greater than or equal to 0, which means x squared plus y squared has to be less than 25. What are these points? What points are described by this inequality? If I had equality x squared plus y squared equals 25, so part of those points, those where it's equality actually, are on a circle. That much you should remember from analytic geometry. It's a circle with radius 5 in the xy plane. Now, less than x squared plus y squared is less than 25. Where are those points? The distance from the point to the origin is evidently less than 5. So those would be the points inside the circle. Sorry, the shading went a little bit out of the circle. What I meant was the circle and its inside is the domain. Because as soon as we step outside the circle, we get the square root of a negative number that, of course, does not exist. If you're interested, in case you're interested in the graph of this function, just imagine z is 20, z squared, sorry, z is the square root, but z itself is 25 minus x squared minus y squared. So basically what you have is x squared plus y squared plus z squared equals 25. You might guess what it is. It's half of a sphere. It's a hemisphere. Because here from this we see that z has to be greater than or equal to 0. This equation describes half of a sphere, half of a spherical surface. So basically the graph, the whole situation should look something like this. We have this domain, which is a circle in the xy dimensions, in the xy plane, and then the whole graph would actually be a hemisphere, half of a sphere, half of a sphere, like this. That would be the graph of this function. So this is the thing that you might see actually next semester as well, because in this way, with rather comparatively simple equations, it is possible to describe spheres, cylinders, cones, the simplest, let's say the basic, most familiar surfaces. We did not look at those in analytic geometry, in three-dimensional surfaces other than planes. However, we can use functions of two variables to describe those, and even more complicated equations that are not exactly functions, but something more than functions. All right, so what are the partial derivatives of explicit functions? Let me see. All right. What we see is delta x of z. Remember what was delta y? We had in 2 dimensions. I'm going to use the comparison, the analogy with 2 dimensions. The delta y was, we had a point, x0. We step out of this point by the distance delta x, and we actually see how the function changes. That was delta y corresponding to this step in the x direction, on the x-axis. Now with the function of 2 variables, so we are discussing 2-variable function. However, it is possible to do or to imagine abstractly the same thing with functions of higher dimensions as well. So if we step out, this would be if we step out of our point in the, okay, let's see. I will try to make a sketch now. That's going to be a bit strange. So this is the point, x0, y0. We have a point on the graph. So basically it's z0, that's the function value, If I now step out of my point in the x direction, so this would be, for example, this would be this delta x. And then I compare how does my function value actually change when I step out in the x direction? That would be this delta z in x direction. See that x is a smaller one. It's below, it's like an index. It means we compare the function values while we step in the x direction with respect to the x direction. So that would be the function at the new point, x0 plus delta x, but y does not change, minus the function value at the original point, x0, y0. So we change only this is the comma, we only change the x value. We make a small delta step in the x direction, and this would be the change of the function. This would be the change of the function value. Oh, we are here, sorry. We are moving in the x direction. I actually messed up my diagram. I messed up the picture. I'm sorry. I will erase this part because this was a piece of the y-axis as I drew it. So I will just the z-axis. All right, I will do it like this. So if I step out in the x direction only, so this is how I compare. This is how I compare the function values. I compare the function values as I move out of this point in the x direction. Similarly, delta z in the y direction, again, y is a small, like an index, a smaller one, like subscript. If I step out in the y direction, again, I compare, I had this basic, I compare how does my function value change here. And you see, it's possible that from this point, if I step in the x direction, my function changes, let's say, in a positive direction, it becomes greater. But if I step in the y direction, the function becomes lower. The function becomes less. So this would be x0 without change, but y0, we step out by delta y, and again we subtract the function value at the starting point x0, y0. And if I want to see the complete change, that would mean stepping out in both directions. That would mean stepping out in both directions at once to some other point. So we make, let's say there's a x component and a y component to my step out. And then that would be the total change when I step in this combined direction. And that's something else again. This means that we change both variables. We step out of both variables and subtract again, as always, the original value of the function. So these would be the increments of the function of two variables in x with respect to x and with respect to y in two different directions. And because we can imagine a surface, where stepping out in one direction, we decrease the function, and stepping out in another direction, we would increase the function, then which is the correct way to do this? And if we step in both directions at once, how do we know? How can we know what's going to happen? This is we will see examples of surfaces a little bit later, but to imagine what it might look like, you could imagine the saddle surface, so where the curvature is different in different directions. So imagine this saddle surface. And if you step, for example, in this direction, you see that the function increases. If you step out in this direction, perpendicular to the first one, you see the function decreases. So you can imagine a situation like this. Or it might be that in both directions, the function does increase. So here we have, I skipped the zeros here because from any point xy, we can step in the x direction, we can step in the y direction, or we can step just in some direction which has a vertical, an x and y component. Now, how to define the derivatives? the derivatives can be defined exactly as we do with a single variable function, except that now we see that the function might be increasing in one direction, decreasing in the other, which means there's more than one derivative possible. So we define the derivative with respect to x, still with the limit when we step in the x direction, so that would be delta x tends to 0, and we will have the delta in direction of x, of z. So we change the z, we consider the z change with respect to x. In other words, I can rewrite this again. Tends to 0. This would be the z function at the point x plus delta x y minus z originally at x y, if you like, divided by delta x. Similarly, the partial derivative, yes, partial, because it's only partially true, it only works in one certain direction. The derivative in the x direction can be found if we look at the increment of the function as we make a small step in the x direction. But similarly to this, in the y direction, of course, delta y tends to 0 would be z if we leave x as it is, but we step out in the y direction, minus the function value at the original point divided by delta, of course, of y. And both these situations take place when the step tends to 0. Delta x tends to 0, so we take a tiny minuscule step in the x direction, and we see what happens to the function itself. So it might be the slope, but it's only in the x direction. And in the y direction, we could say it's the slope, but again, only in the y direction, z depends on y. We generally don't use the word slope when we talk about partial derivatives. It is simply the partial derivative. We always say with respect to which variable. So the partial derivative with respect to x and the partial derivative with respect to y, we saw what happened. And of course, the notation, when we find the partial derivative with a short manner of writing, we write with the prime notation and we'll use x as a small index. So z prime, z derivative with respect to x, f derivative with respect to x. But we could also use the dz by dx, dz by dy notation. Only see the letter d looks different. We don't write it like dz by dy, we write d like this, a special kind of d. We still say dz by dx, but it's a different d. It's only used for partial derivatives. Only used for partial derivatives. If I write d with a regular Latin d, it simply means that this is the regular differential. Dz by dx, that would be a single variable function. We don't use that for function of more than one variables. So we write this dz by dx, dz by dy. Yes, that is possible to use this notation. Just make sure that you use it correctly. And when we find the partial derivative of a function, we always write down with respect to which variable. So in this Leibniz notation, it's obvious that we do this. But even when we use this dash notation, this prime notation, we show which variable we are actually using. So how to do it practically? Remember what happened. We step out in the x direction, but at that time, the y value is the same. It stays constant. So we use this idea when we are finding partial derivatives as such. In other words, when we are finding the derivative with respect to x, then y is held constant. So we imagine that y is a number, a constant, a coefficient, if you like, in this case. So, all right, I will write this notation, dz by dx, so that it's very clear with respect to which variable we are differentiating. The derivative of x cubed is 3x squared. Y is a constant factor, you know, it remains in the derivative. The constant factor remains with the derivative. Plus, now, 3y squared, with respect to x, at the moment, it is constant. Derivative of constant is 0 because we are differentiating by the other variable, minus 5xy. Okay, x derivative is 1, 5y is a constant. So 5y constant times x derivative is simply 5y, and 8 is a constant, so its derivative is 0. So the derivative of this function with respect to x, the partial derivative, is 3x squared y minus 5y. Now doing the same, differentiating with respect to y, now we will imagine that x is a constant. X is held constant. So we will do dz by dy. Let's see, y, x cubed is a constant, so constant times y, like 5y, derivative is simply the constant, so x cubed, plus 3y squared. Now we are differentiating with respect to y. Y is the independent variable, so we have 6y. Now, we are differentiating with respect to y, so 5x is the constant, or minus 5x in this case, minus 5x, and y, and 8 is a constant, its derivative is 0. So you see, we have two different partial derivatives. The difficult part, so basically they are as easy to find or as difficult as you find the differentiation in a single variable functions. My aim is not to give you very, very complicated functions in the two variable functions. So the functions will be comparatively less complex, comparatively simpler, because there's the main difficulty in two variable functions. If you are okay with basic differentiation, the main difficulty is remembering this is now a constant, this is now the variable, holding two the separate things in your mind. So this is a good practice on focusing your thinking, on your memory, short-term memory, on dealing with these things, because when you differentiate partially a two variable function, and sometimes we will have a three variable function to differentiate, you have to remember that this is the variable, the others are simply constant factors. So that's the, I guess, the difficulty. The others are perhaps not so much. Okay, more examples. This is a big function to differentiate. This is a big function to differentiate. First of all, it's a composite function. It is arctangent of x over y, okay, x over y to the power minus 1. It's not the inverse function, it's exponent minus 1. So we see we will have the chain rule. So let's try to differentiate by x. First of all, chain rule, we differentiate the power minus 1. So it will be minus 1, and the arctangent of x over y is now to the power minus 1, that is minus 2. Chain rule. Next, going inwards, the next function to differentiate is arctangent. With respect to this quotient, the derivative of arctangent is 1 divided by 1 plus this squared, so x squared over y squared, times. Finally, now we differentiate x over y, this fraction, but with respect to x. So remember that in this case, if we want to differentiate it with respect to x, we can do it separately if you like. Let's remember it's 1 over y times x derivative with respect to x, because x is the variable. 1 over y is a constant in this case. So it's simply 1 over x, 1 over y, sorry, 1 over y. Now to simplify this whole thing, we will see we have minus 1 divided by arctangent squared of x over y. I'm now using parentheses because I don't want to make a confusion with a square. In principle, this is not strictly required. You don't have to use parentheses if it's simply arctangent of a quotient. I was using them so that there's no misunderstanding. Now for the next part, I don't like fraction of a fraction. A fraction of a fraction is not something I like. So I will, let's say, multiply and divide the numerator, or basically multiply and divide this by y squared. So I will have y squared divided by y squared plus x squared. I multiplied, gave an extra factor y squared, and then of course I have 1 over y, which means, yes, a little bit of simplifying. So the final result is, so we see this is a double chain rule, or triple if you like. First of all, we differentiate the exponent minus 1. Next, we differentiate the next interior function arctangent. And then we differentiate the function that is still inside the arctangent with respect to x. You might notice that we did not differentiate with respect to x. The power minus 1 is not with respect to x, it's with respect to the arctangent. Arctangent derivative was not with respect to x. Arctangent derivative was with respect to this. And finally, this fraction can be differentiated with respect to x. The derivative with respect to x shows up only here, only in the very last step. And so the result, minus y divided by arctangent square of x over y times x squared plus y squared. And oh, that's it, nothing else. This was y, this is not a 4. So you see, we have, let's say this is the derivative of our function with respect to x. Now to do the same with respect to y, let's see, I might actually attempt to do this. Okay, to do this here, because I think I can manage to squeeze it in. Why? Because you see, when I differentiate the same function with respect to y, first of all, the derivative of power minus 1 is exactly the same. The derivative of arctangent is the same. So we can, in principle, write minus 1 over arctangent square of x over y times 1 divided by 1 plus x squared divided by y squared. So the first two links of the chain in the chain rule are the same, because we are differentiating operations power minus 1 and arctangent, which depend on whatever is inside. Now we have to multiply by the derivative of x over y with respect to y. So that would come here, evidently. X over y with respect to y means that x is the constant and y is evidently to the power minus 1. And then we differentiate it with respect to y, which becomes, of course, x as a constant remains. Well, y to power minus 1, we see we need minus 1, and we need to divide by y squared. So this would be minus 1x y to the power minus 2. Remember what happens to the exponent in this case. So as a result, we see that this is negative times negative is positive, so it's just x, divided by arctangent square of x over y. And now if I multiply these, 1 times y square is y square, fraction times y square is just x square. So we have exactly the same second factor in the denominator. Now, if you compare the two partial derivatives, they're surprisingly similar. And the reason why they are surprisingly similar is that we don't start differentiation with respect to x or with respect to y, this part. We don't start it until the very last step. It's only here that the differentiation with respect to x or to y happens. It's only at this point, it's only there in the last step. It's not always true, but in this case, we see that all those operations lead us inwards, more and more inside, and it's only inside at the very center, at the core of this function, that we finally see the two independent variables. In other functions, of course, it's not the case. So basically, this would be the most difficult example that I'm giving you. I'm not going to ask anything more difficult than this of you. Now let us have more partial derivatives of implicit functions. Implicit functions, an implicit function is a function where, just like with a function of one variable, we simply have a mess. We simply have a mess. We have an expression. We have an expression where x, y, and z are tangled together, and we still consider z is a function of x and y. So what we do is we find the three derivatives separately. The derivative of this whole expression with respect to x, the derivative of this whole expression with respect to y, and the derivative of this whole expression with respect to z. Even though z is a function, in this case, we are not using the chain rule here for z. We simply differentiate not the function z at the moment, but we are differentiating the whole big expression. Like we could say a meta function, a function that is greater than our simple function z. And then when we have found all three partial derivatives of this expression, then the derivative of z with respect to x is the opposite of derivative by x divided by derivative by z. And derivative of the function z with respect to y, we take the derivative of the big expression by y divided by the derivative of the big expression by z, and the minus sign in front. So that's a specific method for derivatives of implicit functions. That is for functions where we either do not want or it's impossible to untangle, to express z. Sometimes it's just too complicated. Sometimes it's just not worth the effort when we can do this by, let's say, by little bits. The example will be this. So first of all, we need the expression with respect to x, y, z on one side. The right-hand side has to be 0. So this means that we basically, first of all, rewrite this. Everything, we bring everything to one side of the equality sign. So z cubed plus 3xyz minus 8 minus xy squared minus x squared y equals 0. Now this is the f expression on the left-hand side, and now we will simply differentiate it by each variable with respect to each variable separately. So we differentiate the whole expression with respect to x. Z, in this case, we assume that f is the function to differentiate. So z is a constant because we are only differentiating by x. The whole expression is differentiated by x. So at this moment, we think z is constant, y is constant, only differentiate by x. So here, x derivative is 1. So what remains is the constant factor 3yz. It is a constant, no worries. Minus x derivative is 1, y squared is a constant. Here, x squared derivative is 2x, y is a constant factor. There you are. So in principle, what I would expect you to do is to differentiate a mix of powers, maybe some exponential functions, some simpler things, but not much. Now, let's take the same expression, the same big F function, differentiated by y. Again, z is a constant, 3xyz. Derivative of y is 1, 3xz is a constant, 3xz. We have taken out y by differentiation. When we differentiate y, we get 1. It is a constant. Y squared derivative by y is 2y. X is a constant, so 2xy. Here, y derivative is 1, x squared is the constant factor for it. And the derivative of this expression with respect to z, we see it's 3z squared, and this will be differentiating by z, 3xy, the constants, plus 3xy. And now to find the derivatives of this function, the partial derivatives of this function with respect to x and y of the function z, not of the big expression. So now I will write dz by dx will be minus. Now we take the derivative by x. So it's 3yz minus y squared minus 2xy, and divide by the derivative with respect to z. So that is 3z squared plus 3xy. And again, yes, this partial derivative is expressed using the independent variables x and y, and also using the dependent variable z. It's similar to what we did with the implicit functions, actually, for the one variable function. This is something that we can use for a single variable function exactly in the same way, in a similar way. Hopefully, we might have enough time to have a look at those examples as well. At least one of them I have. Now, minus in front. And so we have derivative with respect to y of the big expression, 3xz minus 2xy minus x squared, divided by 3z squared plus 3xy. So if we do this for a single variable function, so if we have y is a function of x, but we have an expression where these two are mixed together, we had a method for implicit differentiation using the chain rule. Remember, we had implicit differentiation, use chain rule, express it as a quotient. So now we can do it similarly to these functions of two variables. In other words, we can find the derivative of the big expression with respect to x. We can find the expression of this big expression with respect to y, and the derivative. Okay, this would be the regular derivative. This is the regular d. This is the regular d because this is not partial. This is for the old functions, for the old regular functions. So I can write dy by dx would be minus f derivative by x divided by f derivative by y. So the pattern is the same. And if you have a function of three variables and an implicit one, evidently you have to find 4 partial derivatives to construct the 3 derivatives of the given function. So in principle, now you have a new method for implicit differentiation in one variable. So we could do using the chain rule, we could do it using the chain rule, or we could do it this way, and it is possible to prove that the result will be exactly the same. It cannot be anything else. It is possible to prove, to demonstrate analytically by transformations that it would be exactly the same thing. If we do this, or if we take the differentiation of both sides, remember we took both sides, differentiated them using chain rule with respect to x, but using chain rule, and then we expressed the y derivative. So this is, of course, not exactly the same thing, but the result and the expressions would be exactly the same. So that's a new method if you like to use this one. All right, some exercises now, and then we also need to consider higher order partial derivatives. So what matters here is, of course, the distinction. If we want to differentiate with respect to x, we think, okay, it's 1 over y times x, the first part. And differentiating with respect to x means x disappears, we have 1 over y. Now the second thing is y squared times x to the power minus 1, because we are differentiating by x. So this will be minus, then we have y squared, which is the constant with respect to x. It's the constant. And x to power minus 1 when differentiating becomes minus 2. So x squared there. So this will be y squared times minus 1 x to the power minus 2, using the rules of differentiation of a power. Y squared is the constant. That's why it doesn't change at this point. And if we want to differentiate with respect to y, now we see 1 over y to the power minus 1. Y to the power minus 1 means the sign will change and the exponent will become minus 2. So x is a constant, then we gain a factor minus 1, and y, instead of power minus 1 at the beginning, becomes to the power minus 2. So minus x divided by y squared, because this is now evidently x times y to the power minus 1 derivative, reminding you x is a constant times minus 1 y to the power 1 less. So this is this. Now, if we differentiate this by y squared derivative by y is 2y, and 1 over x is a constant. In this case, we see it as 1 over x times y squared. And if we differentiate it by y, and here we also differentiate it by y, we see 2y, but still divided by x, because this is the constant. So we have 2y divided by x. These are the two partial derivatives. In principle, not so complicated, but you have to be very careful with differentiation with respect to the particular variable. Remember that the other one is constant. It would be a good idea to separate, as I do here. It's not a requirement, but it makes things easier if you attempt to separate them. Separate the constant factor, well, constant conditionally, the current constant factor separated from the variable with respect to which we are differentiating it. This function is typically a difficult one, because why? Because people tend to be very confused. So one of these, let's differentiate. Okay, let's write it like this. Will be easier if we use Leibniz notation. Derivative by the variable u, and derivative by the variable v. It's actually easier to write with prime when we differentiate with respect to x, with respect to y, when the variables acquire new names. When we have variables named differently, then perhaps it's easier to write it like this because it draws your attention to which variable we are differentiating with respect to. Now, let's think. If u is the variable, then v is the constant. Think in terms of x to the power a, variable u to the power constant. So when we differentiate a power of the x, this is a x to power a minus 1. Hopefully everybody knows this by heart by now, which means that now we can write the exponent is v, so we have v times u to the power v minus 1. Now, if I have to differentiate with respect to v, then I assume that u is a constant. So in this case, v is supposed to be constant, and in this case, u is supposed to be a constant. This means the base of the power is like a constant, and the exponent is like the variable. Remember that these are two very different functions. Remember that the derivatives of these two functions are very different. So this is a to power x times ln of the base a, which means we still have u to the power of v, but we also multiply by the logarithm of base, ln of u. ln of u. So two basically very, very, very different partial derivatives. Different because you see the principle of differentiation is very different for these two types of function. This is a very common error. People tend to confuse which is which. So be careful, and before you jump into differentiation, think very, very carefully. Next one, this should be very simple. So derivative of u with respect to s and derivative of u with respect to t. When we differentiate with respect to s, see, it's a simple power. S squared, derivative is 2s. So we have 6s e to the power t. And if we differentiate with respect to t, then 3s squared is a constant, and as a constant factor, it remains there. E to power t derivative is e to, oh, sorry, it was s. I'm sorry. Okay, this is not t, this is s squared. So s squared e to the power t, the function itself. So in principle, as long as you can keep in mind, and sometimes perhaps you just want to write. So at this moment, t is constant. We are holding, it's not a constant, it's a variable. But when we are differentiating partially by one variable, we are holding it constant. It's not constant by default, but in this case, while we are doing this, we are holding it constant. While we are differentiating partially by t, we are holding s constant. They are variables, but at this moment, we keep it constant, we work with the other one. So that's basically the main difficulty. The main difficulty is separating these two things in your mind. Needs a little bit of practice, which is why you should do the practice exercises from the file as well as perhaps the homework, which is not big, but well, complicated enough. As you have noticed, the homework is usually more complicated than what you get in class in the test. Okay, so now this is easy. I can use the usual notation because it's x and y. Now see, it's x to power minus 2. So derivative of x to the power minus 2, you can always do it separately. You can always do it separately, is of course minus 2, x to the power minus 2 minus 1 is minus 3. So I can just write minus 2 divided by x cubed. Here, 1 over y squared is a constant differentiating x, 1 over y squared. Hopefully it's clear enough. So you don't have to write, but we think like 1 over y squared times x, derivative with respect to x still. And here as well. Now the other one, the other partial derivative with respect to y. This is a constant for y with respect to y. This is a constant, so nothing. And here we have x times y to the power minus 2. If we differentiate with respect to y, we still have x, we have minus 2, we have y to power minus 3, similar to the previous. So we have minus 2x divided by y cubed. So the main difficulty is, as you see, don't confuse things. Remember what a constant does, and then you will do just fine with this. All right, another one, quotient. So we have
Professor,
to, yes.
can you move back to previous question?
Okay, there you go.
Here it shouldn't be. It is 6 minus 6. It shouldn't be. It's minus 6.
Wait. Oh yes, it should be minus 6. I was looking at this. Yes, thank you. It is minus 6. This is minus 6. That's correct. All right. Now this quotient, because in both parts, in the numerator and in the denominator, we have both x and y, we have to use quotient rule in both cases immediately, just taking constants differently in both cases. So we would have u derivative with respect to x, quotient rule. Now I will write slowly. 2x minus y derivative with respect to x times x plus 2y without derivative minus 2x minus y without derivative, x plus 2y differentiate with respect to x. This is important because otherwise you might get it wrong if you don't mark which variable you are using. And here we have x plus 2y squared. So what we have is, this is derivative by x is just 2. So we have 2x plus 2y minus, now derivative by x is simply 1 because 1 plus x plus constant derivative is 1. So it's 1 times 2x minus y divided by the square. So we have 2x minus 2x disappears. 4y plus y is 5y after opening parentheses and simplifying. X plus 2y squared. And for the derivative with respect to y, we see 2x minus y without derivative times x plus 2y derivative with respect to y minus 2x minus y derivative with respect to y. Wait, the other way around. This was with respect to y and this was without. Well, I wasn't thinking, sorry. I was thinking about something else. I let my mind wander, which is not a good thing. Need to focus. 2x minus y, x plus 2y derivative with respect to y, and divided by x plus 2y squared. So similarly, we will have the derivative by y is minus 1. So it's minus 1 times x plus 2y. The derivative of this with respect to y is 2. So we have minus 2 times 2x minus y divided by the same square. And so we see minus x minus 4x is minus 5x. minus 2y, and here we have plus 2y, they disappear. And we divide by the same old square of the denominator, x plus 2y squared. So you see, the process of differentiation by itself is not so very complicated. The complicated part is focusing your attention to what you need to focus on. That might be the difficult part. Here we have another function. Here we have another function, so we can write z derivative with respect to x is, now let's see, this is a constant in this first case because y is a constant, so it's worth reminding. If y is a constant, the cosine y is a constant, so it's a constant factor. Derivative of e to power x is e to power x. Fine. Now here, e to power y is a constant because y is a constant. Sine of x differentiated by x's cosine. So we have e to the power x, e to the power y times cosine of x. That's the derivative with respect to x. In other words, we kept these two factors constant and only differentiated e to power x and sine x. Now, if we keep x constant and differentiate by y, then e to power x is a constant. We differentiate cosine of y by y. That's minus sine of y. So I take minus and I write sine y. Here, sine of x is a constant. And e to power y derivative by y is e to power y. So you see these two derivatives again, interestingly, in an interesting way, not exactly symmetrical, but there is a similarity, of course, because the function was looking similar to itself at the beginning. So you can even use the differentiation as you see in this kind of function. The good part for this was, you see, the variables were separated in each of the products. E to power x separate from cosine y, e to power y separate from sine x. They were not mixed together. We didn't have e to power x plus y, although you could. We didn't have e to the power xy, so we had separate e to power x, separate cosine y, separate e power y, separate sine x. So that makes it easier, of course. Now here we have a slight mixture. Let's consider this one. So product rule for x, because both factors contain x and y is the constant. So product rule for this, x squared derivative is 2x, e to the power left as it is, plus x squared not differentiated, e to the power derivative, e to the power x squared plus y squared times, remember, the derivative with respect to x of the exponent. The derivative of the exponent, x squared plus y squared, is 2x. We are differentiating with respect to x only. So we can actually simplify it somewhat. It's 2x e to the power x squared plus y squared, and we have 1 plus x squared in parentheses. Okay, to simplify it a little bit. And as for the derivative with respect to y, it's easier because x squared, remember x is a constant now, so x squared remains, it's the constant factor in front. Now times e power derivative is the same old e power times the derivative of exponent, but now we are differentiating with respect to y. So the derivative of the exponent with respect to y is just 2y. So it's 2x squared y times the power of e. more or less. So you see, basically not so very difficult. I really saved the really difficult example with the arctangent for the beginning. I did it at the beginning. So basically you should not expect anything much more difficult in the test, sorry, in the examination, nothing much more difficult than this. Basically what is the thing that I will be testing is whether you can keep them separate in your mind, X and Y separate in your mind, and then let's say understanding of definitions. And of course, remember that your formula sheet is already in Ortus. Download it, print it out, keep it in front of you as you do your homework, as you prepare for the midterm examination. It's helpful. Arc sine of something horrible. All right, we can skip this because I'm not going to give you anything very difficult as this in the examination. However, in the lecture transcript, this, of course, the answer to this is there. I want to jump ahead a little bit because we have still one more thing to discuss or two. So for implicit function, an example for the implicit function. So in principle, yes, it would be easy to express z. See, we only have z in one place. We could easily move everything else to the other side, divide both sides by e to power x, and we would have an expression for z using x and a, x and y, and a is a constant. Of course, a is a constant, but possibly for the implicit function, if this is, so we could say, okay, let's take minus a equals 0, taking everything to the left-hand side. Also notice that we have, okay, some people are coming very late, as is their habit. A is a constant, which means when we differentiate by x, by y, by z, it will disappear. So the derivative by x will be e to power y constant times x. Derivative is simply e to power y plus e to power x. Derivative is e to power x, and y is a constant. Again, simple. Z is a constant times e to power x as it is, and that's it. Derivative by y, the big expression, just let's remember that z is supposed to be a function of x and y. So we will express it in the end, the partial derivatives of z. Now by y, x is a constant, e to power y derivative is e to power y plus y derivative is 1, e to power x is a constant. So this. Here, z and e to power x are both constant with respect to y. We are differentiating by y, so this is a constant. That's it. And a is a constant universally. And finally, differentiate by z. Differentiate by z. This is a constant. This is a constant. Nothing doing. Differentiate this by z is e to power x. So you see how simple will the actual derivative, the partial derivatives be. So dz by dx, remember, we take minus, we take the f derivative by x, plus y e power x plus z e power x, divide by, evidently, just by e to power x. We can simplify this. We can simplify this. We see that it is minus everything negative, e to the power y minus x. Now remember your elementary mathematics. When you divide two powers with the same base, you subtract exponents. Plus, now this divide by e to power x is just y, and divide this is just z. And differentiating z by y, we do the same thing. We do the same thing. It will be, so minus x e to power y plus e to power x divided by e to power x. So we can write this again, minus x times e to the power y minus x plus 1. So these two partial derivatives can be written like this. Of course, as I said, in principle, it is possible to say z is evidently a minus x e to power y minus y e to power x divided by e to power x, like this, and then differentiate it. Well, it is possible. It is possible to simplify it and differentiate and get the same, exact same expressions. Of course, the z expression should be added in there. So it's possible sometimes, as you see, it is possible to express, but I would say that differentiating it this way, in this form, is easier. It's easier to look at this in one line, each derivative in one line, then you simply write down the fraction, and the fraction is not so difficult to simplify. This is something very similar. We can do the implicit differentiation again in the same way. So the derivative by x. Now remember, z is a constant, so it's like a to power x, which means it's still the same times ln of base z plus x to power y, where x is the base, x to constant power means y acts as a constant, and 3z derivative is 0. Similarly, derivative by y, this is a constant, x to power y derivative by y, it's again like constant to power variable. So this is like a to power x. So again, it's x to power y ln of x, and 3z derivative is just a constant, derivative is 0. And finally, the derivative by z. So variable z, x constant. So we have to use the rule x to power a, variable to power constant. Constant times z to power x minus 1. Next is the constant derivative 0 and plus 3. And then you can do the same. I will not rewrite it, but the z derivative by x was, remember, minus f derivative by x over f derivative by z, and z derivative by y is again minus f derivative by y divided by f derivative by z. We have a formula for that. All you have to do is just take these expressions and just rewrite, finish writing. That's simply the matter of copying the correct functions. All right, here we are. Now we have some 14-15 minutes. Okay, it will good. It will be good. Now let's try the single variable. Let's try the single variable. So we are thinking in terms y is some function of x. Normally we will have used the chain rule. If you remember, we used the chain rule to differentiate both sides, then rearrange the terms, move all the y derivatives to one side, the terms without y derivatives to the other side, taking the common factor out, dividing, and so on. But we can use this very same expression. So let's say that f of xy is this expression. Of course, a square is a constant. I will rewrite it like this. As always, move everything to the left-hand side. So now I will take the f derivative by x will be x derivative is 2x, y square constant with respect to x, so nothing, plus next ln derivative. All right, 1 divided by x squared plus y squared times the derivative of the interior expression by x. So it's 2x, and a square is a constant. Now f derivative by y, similarly, very symmetrically, as you can see, x derivative 0, y square derivative is 2y, plus ln derivative 1 divided by x square plus y square times the derivative of the interior expression by y. So it's 2y. And now the derivative of this function by with respect to x. So df or dy. Okay, I will write dy. dy divided by dx. So the derivative normal is minus f derivative by x divided by f derivative by y. So now it's official. You can use this approach. We started using it for the functions of two variables, but in principle, there's nothing to hold us from doing it with a single variable functions. So now possibly, okay, I will write these as they are for the moment. 2x plus 2x over, no, actually, no, I will simplify. I can take 2x, so it's still a minus in front, sorry, I forgot that, minus in front. I will take 2x, the common factor from these two outside, and I have 1 plus 1 over x squared plus y squared. And I will do the same with 2y here, 2y outside, and what remains in parentheses is 1 plus 1 over x squared plus y squared. If you can notice this, then it's actually very, very useful. And so we see, okay, these can cancel out. So we have basically minus x over y is the derivative of the function y, which depends on x. So you would basically get the same thing if you did it by chain rule. At the moment, I simply don't want to waste the time for that. You may notice that this is probably easier. This is probably simpler. So you would be advised, if you see something like this in your examination, then maybe this is the method to use, as I said. And now higher order partial derivatives. Higher order ordinary derivatives, regular derivatives, common derivatives. Remember, we simply took the derivative and differentiated once more. Now let's try to do it here. So let's do z derivative by x is, now remember, y squared is a constant, so this is 2, it's 2y squared minus y is a constant, differentiating xy gives us simply y. 3x squared derivative is 6x, 4 derivative is 0. And the derivative by y is y squared derivative is 2y. So we have 4xy minus xy derivative with respect to y is x. 3x squared is a constant for y, 4 is a constant for y. All right, these are the regular first order partial derivatives. Now, what about the second order? How do we know how to differentiate these? So I will take this, differentiate it one more time, and I get, okay, y squared, this is a constant, 6x derivative, all right, 6. I could take this, differentiate one more time. Now I have y derivative is 1, so constant for x, and that's it. Now, is this it? Is this the end? Well, no, because as I started automatically, sometimes we assume automatically that we go on differentiating by the same variable, but who is to say that we cannot use this first order derivative and differentiate it by y for the second time? So I could do z derivative by x differentiate second time, but by y. So this is the so-called mixed second order partial derivative. If I differentiate this by y, I see 4y minus 1. If I differentiate the first derivative by y and then take this and differentiate by x, again mix them, I get C 4xy differentiate by x, you get 4y minus x differentiate by x, you get minus 1. Interestingly, these are equal. So what we see here, we see that in principle, we can differentiate as many times as we like, but we need to keep track of the variables. Are we differentiating all the time by the same variable? Are we switching, mixing the variables? That's the difference. And so here you have the higher order partial derivatives. You can take the derivative by x and differentiate it again by x. We write it just like this, yes, z second derivative both times by x. Or you can write it as the second order partial derivative d2z both times by x, by dx squared, divided by dx squared. Similarly, you can write second order derivative mixed, take x derivative, differentiate by y. You see, you write it like this. I will not repeat by hand. You can take the second order derivative by y and start differentiating by x, so second order derivative y then by x. And we write it, yes, we observe the correct order of differentiation. So we do write d2z divided by dx dy, and in this case, I write d2z divided by dy dx, minding the order. And finally, of course, second order partial derivative both times by y is, of course, d2z by dy squared. So a question about these second order mixed derivatives might arise. Basically, there is a rule. If these derivatives exist at some point, then at that point they have to be equal. The rule is, if these derivatives exist, then they are indeed equal. So basically, one possible task for your midterm or final examination might be find all first and second order partial derivatives. That means you don't have to find 6. You have only 2 first order partial derivatives for a 2 variable function, but for the second order partial derivatives, you might see that they are mixed. They are mixed and the mixed ones are identical. So there are only 3. We can write 4 of them, but because 2 are identical, we have 3. So basically, you might have a task like that. Find all first and second order partial derivatives, which means you will need to find 5 partial derivatives. Start by the first order derivative and then go on, differentiate them one more time by each variable. 5 derivatives. So that's one task. I'm simply because we are not having a test for this unit, I'm simply telling you in advance that one task one kind of task could be find all first and second order partial derivatives. For example, with this, find all second order partial derivatives. So the first order derivatives, first of all, you cannot find second order derivatives without finding the first order derivatives, of course. So ln of function derivative, remember, is 1 divided by that function times the derivative of the interior function, but this interior function differentiated by x is just 2x. And in the case of y, the same goes below the line, but above the line is just plain 1. Derivative of y is 1 by y. And now the second order. Second order, okay, looks like the quotient rule. All right, quotient rule. Take the by xx, sorry, xx. Both times by x, first of all. This is traditional. So we have the square, of course, x squared plus y squared. Now, this differentiated by x is 2 times x squared plus y minus 2x as it is times this differentiated by x is again 2x. And so we have 2x squared minus 4x squared is minus 2x squared and 2y. So it's 2y minus 2x squared divided by x squared plus y, all of it squared. Second order, well, which way we go? Let's differentiate by y. Perhaps let's take this and differentiate by y, or take this and differentiate by x. Okay, mixed xy is the same as derivative by yx. Both cases are the same, so I will take which is easier. Looks like this looks like simpler differentiation by x. So this is actually x squared plus y to the power minus 1 differentiated by, now we have to differentiate it by x. So we have, of course, power minus 1 means minus 1 times x squared plus y power minus 2 times chain rule. Chain rule is x squared plus 1 derivative by x, 2x. No, these are not second order exact differentials. These are second order partial derivatives, as the title says. Exact differentials next time. Differentials will be next time. Today I am focusing on techniques of differentiation, how to differentiate. Differentials will be next time. Derivative and differential, as you know, is not the same thing. No, not this. These are not exact differentials. No, you're asking because you saw the homework. Okay, next time. And so we see minus 2x divided by x squared plus y squared. And finally, derivative, double derivative, second order derivative, both times by y, 1 over something, 1 over something. So I can write x squared plus y to the power minus 1 differentiated by y. So power minus 1, as always, minus 1 x squared plus y power minus 2 times the expression differentiated by y is 1. So there we have different derivative, second order partial derivative both times by x. Here we have second order derivative once by x and second times by y, and it's the same both ways. You only have to do once. And finally, second order partial derivative both times by y. So in principle, something like this, if you have something like this in the exam, this is what it might look like, your solution, for instance. Okay, second order partial derivatives, mixed partial derivative. Okay, just 2 examples remaining. Very good. So I will just finish up as quickly as I can, so that you have the idea. What happens meanwhile, just a moment. Okay, people are coming online, going offline. Anyway, yes, please sign for a second time, because otherwise I do have a feeling that some people don't hear. Please sign your name one more time, and I will remind you of what I said later in a couple of minutes. So the derivatives, x to the power y, remember we already did them once, only we had other functions. So by x, if x is the variable, we have y times x to the power y minus 1. If we differentiate it by y, then we have like an exponential function, x to power y times ln of the base x. Now, if I have to do it one more time, second derivative both times by x. Second derivative both times by x. Y is a constant. Now, y minus 1 is the exponent. It again becomes a constant factor. And now x is to the power 1 more less. It's this, 1 more less. It was y to power minus x to power y minus 1. Y minus 1 becomes the factor, and y minus 2 is the exponent, that is 1 less, reduced. Now, second derivative, mixed. Mixed, we can choose whichever we like. Well, mixed. If I take this and differentiate by x, I have the product rule. If I take this, differentiate by y, I still have product rule. So it doesn't really matter. I will take the first one. So I will take y x power y minus 1 derivative by y. So x derivative by y. So I am taking this. I am taking this. Product rule, y derivative is 1 times x power without derivative plus y without derivative times x power with derivative. Now, y is the variable, x is the constant, so we differentiate it as if we have a to power u. X plays the role of constant at this moment. If you have difficulties, actually it's a very good idea to write down. We assume that x is a constant at this point. It's not a bad idea. So we would have still the same exponential function, x to power y minus 1 times ln of x, because ln of the base, times the derivative of y is 1. I'm writing it, but in principle, I'm simply reminding you that you cannot forget the derivative of the exponent. Or, well, you can, but you may not. It's not a good idea. So we can write, evidently, x to the power y minus 1 in parentheses, and outside we have 1 plus y ln x product, like this. That's the mixed derivative. And finally, both times by y, we have ln x as a coefficient because it's a constant at this moment, x to the power y, again, as if we have an exponential function. So it is x to power y times ln of x. One more time. So basically what we have is x to power y times ln x. And the logarithm is squared, not x, but logarithm. So you see that even these messy functions can be differentiated twice. I would like to remind you to be very careful, especially when you do the second order derivatives. Remember the change of variables, So basically you can get the mixed derivative in two different ways. It's up to you which way you choose, but then you have to keep it strong in your mind. It's all the problem of focusing your thought. Okay, and finally the last one, yes, this is possible. Fourth order derivative, differentiating several times. Basically the order of differentiation doesn't matter. But see, this would be the first time by x, then twice by y, and finally by x again. This is what it says. However, if you write the order of differentiation does not matter, then you can choose as long as you differentiate 2 times by x and 2 times by y. So I would start by, let's start differentiation by x. So we have 2x cubed derivative 6x squared and multiply by y squared minus x derivative 1 plus x derivative is 1, so y cubed. Now it's up to us whether we differentiate by x or by y. I vote for x. Why? Because then these two terms will disappear. If I differentiate now by y, I will still have this term and this term differentiated. But if I differentiate it now, if I do it by x, then actually d2z dx squared is differentiate this by x, it's 12x y squared, and that's it. And that's it. So then I will have third dx squared dy will be y squared derivative 2y, so it's 24xy, and finally d4z dx squared dy squared will be, take this by y, 24x. As long as you write down that this is the same as 4z dx squared dy squared. If you write something down something like this, and probably in the end, because in the process of differentiation you will make the decisions. So if you start differentiation by x, then you look at this and think, is it better now to go on with x or to differentiate by y? As long as you keep the count correct. And finally, for those who came late today, I am reminding you to please, if on Friday you have another test, exam, consultation, or something, well, some appointment at a certain time, like you did, some of you did last week, please inform me. Today, tomorrow, Wednesday, you have 3 days to let me know, because the time of the midterm too on Friday and the groups will depend on that information. If you forget, if you do it too late, then you have a problem. If there's a clash of interest somehow, then you have a problem. It's in your best interest to let me know as soon as possible so that I can set up the examination groups. All right, then, on Wednesday, we will talk about exact differentials. Basically, you don't need much more. Those who want to do it for your homework already, you can look up the lecture files. The exact differential uses these derivatives. You can write down the exact differential. If you have all the derivatives, partial derivatives, then you can write down the correct exact differential. It's only the matter of knowing what to write down. So it should be easy enough. And mostly, for the most part, next time we will talk about what can we do with these derivatives, what information they give us about this surface, about this function of two variables. That's it. Before anybody asks, you are bound to get your marks tonight or tomorrow morning, if anybody is interested. With respect to elementary mathematics, those who will still need to retake elementary mathematics can do that on Wednesday during the elementary mathematics time. We don't have a lecture anymore, but we can have a retake then during the elementary mathematics time. All right, I will see you probably on Wednesday. You will formation tonight or the latest tomorrow morning. And we have one more lecture remaining, one midterm examination, and then we will see what happens. Some of you will need to write the final examination next Wednesday, the 16th. That unfortunately cannot be avoided. Those people who have already failed the midterm examination and the retake probably are those. However, even for those people who know that you will need to write the final examination, it would be a good idea to attempt the second midterm for the sake of practice, to see what kind of questions you can expect. The final examination basically will have the same kinds of questions as the midterm examinations, the same kinds. So nothing really outside our standard situations. All right. So tomorrow we do nothing. I cannot do any retakes every single day. Tomorrow we do nothing. On Wednesday, possibility for elementary mathematics retakes during the elementary mathematics time, and about the rest we can then agree on Wednesday. I hope everybody wrote their name for the second time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 out of 28 people who pretend to be online. That's nice. Assignment. I put the mark in the grade book. So look in the grade book. I write the mark in the grade book and I write a comment that this was a retake perhaps, but it's there. Now they wake up. Now they wake up. Ay, 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 ay. Okay. All right. So please remember to let me know if you cannot make it at a certain time on Friday. I need to see which times are, let's say, the worst to avoid those and so on. Please let me know if you have an appointment or exam or a test or a consultation that you absolutely need, and tell me what it is. Because if it's an exam, I will probably try to make a greater break between the two.